So we'll have the next talk of this session, and it's again Kamesh who's going to tell us about parts 2, 3, and 4.
So just to recap from the last part, so the nice thing about this LPs is that we were trying to find the max of some random variables, and the LP, we didn't use the closed form for the max anywhere. So in that sense, it is nice, and it yields policies with the right form. You get a threshold policy using the dual. But the crucial thing is we needed independence of the random variables. The whole LP business doesn't work if you have correlated random variables. Okay, so part 2, I'll generalize what we did. And say, okay, what were the key things we needed in doing this kind of analysis, and can we do it for more problems? So the feature of this maximum value is what I call a weakly, or what is known as a weakly coupled decision system. And this terminology is from operations research. In a sense, you have like sort of independent decision spaces. You can think of, in the case of maximum value, every box has its own decision space, which is what to do with the box. And there's very few constraints that connect stuff together, right? The one constraint was that you can only choose one box. Other constraint is that you can open only k boxes. There are only two constraints. So a general recipe for such decision spaces would be to write an LP with the constraints on the expected values. And it's important that there be a constant number of such constraints, because when we were doing rounding, we were losing a constant factor that depended on the number of constraints. And sometimes this stuff doesn't work, and you need stronger LP relaxations with a lot more constraints. And I'll come to that later. And if you write such an LP, then you just solve it and use Markov's inequality. And the dual yields, there's more structure in the dual, and you can use it to show various things. It's all high level. I mean, the maximum value, each box has its own decision space. The crucial thing is that the boxes are independent, right? And that was crucial for our LP. And the coupling constraints were these, and the dual yielded a threshold policy. I mean, choose the payoff if value is greater than the dual multiplier. So another problem is what is called stochastic knapsack. Here you can think of a knapsack. You have items. Every item gives you a certain reward if you place it in the knapsack. But the size of the item, instead of being deterministic, is drawn from a distribution xi. So you for every item, you know what its distribution is. These sizes are independent. And you get to know the actual size of the item only after you place it in the knapsack. So you place it, and then you get to learn what its size is. So this has applications to job scheduling, where unless you schedule the job, you don't know how long it took to run. And you have a knapsack with capacity at most b. In the scheduling context, you can think you have a time horizon, you have a time interval of t, and you want to schedule jobs in that time interval. And now you want a policy for placing the items in the knapsack. You want to maximize your reward, the expected reward that you want. And if the knapsack capacity is violated, so an adaptive policy it'll place an item, it takes some size, gives you some reward. Then depending on how much size it took, you could decide to place some other item next, so on. The policy has to stop when the knapsack capacity is violated. So when it places an item and it overflows the knapsack, it stops. And you maximize the expected reward. So it's again, you get a decision tree. Right? And just as before, you can write like this kind of LP, where the variables will be this yj, which is the probability that a policy places item j in the knapsack. There's some zero, it's some number between 0 and 1. So the expected reward of the policy, the reward values are deterministic. So it's the reward of j times the probability that j is placed in the knapsack, summed over all j. This is easy. So what this constraint is saying is that, look, the expected size of the items that are placed in the knapsack is at most b, but because you overflow by one item, you can write it as 2b. You need 2b here because of the overflow business. And why is writing this way correct? Because firstly, the sizes of the items are independent. Okay, so the event that you place the item in the knapsack is independent of the size that you will observe, right? So this is the sort of expected value of the event that, so it's basically if j is placed in the knapsack and it has a certain size, that is the random variable, and you want to take its expectation, but you can decompose that into the probability that j is placed in the knapsack times the expected size, because these two events are independent, the same as before. And again, you're crucially using the fact that the different items sizes are independent. So again, I mean, this, you get an LP, it almost looks like an LP for standard knapsack. You have expected sizes now. And now you can do some kind of rounding using Markov's inequality. You place the items in decreasing order of reward divided by expected size, it will give you something. So in this part, I'm not going to go into proofs and details and so on. It's just okay, at a high level. Okay. So another problem is stochastic matching. And this has applications to things like kidney exchanges, dating sites. So as motivation, think of a dating site. You have men, you have women, and you can send some man I and some woman j on a date. The date succeeds with some probability Pij. Maybe you know Pij up front. You can, I mean, many of these dating sites have these huge feature vectors, and using those feature vectors, they can calculate, okay, if we pair these two, what is the probability it will succeed? Right? So these Pij values are known up front, and it yields some reward Rij. Maybe that's the amount of money they pay to the site. I don't know. Right? So if the match is successful, if you send I and j on a date and if it's successful, then both I and j get removed from your graph because they are done. Right? If the date is not successful, then this edge gets deleted, but I and j continue to remain in the system. Okay, they're still in the site, on the site. Okay. Is it clear now? You want to again. So the input is this matrix of Pij values and the Rijs. And the decision policy is what is an adaptive order of setting up these dates. I mean, you try this edge first, then this edge, then this edge. And trying an edge could depend on which edges you previously tried.
What's the Pij Rij again?
So, okay. Rij is the reward that you get if a date is successful. And Pij is the probability that a date is successful.
Rij is deterministic or is?
It is deterministic. And in the original formulation of this problem, there are also constraints on patience. Like you can also have a constraint that the number of times you can set I up on a date is at most some Ti. After Ti tries, maybe the guy leaves the system. Right? You can have those constraints. It'll all work out. And the goal is to maximize the expected reward from the successful matches. Okay. And so again, it's like you can think of the optimal policy as being some adaptive mess. Again, you can write an LP, which is so Xij is if you take a decision policy, what is the probability that I and j are set up on a date? Okay, it's some big decision tree. Fix some I and j. What is the probability that they were set up? Right now, if you assume that these Pijs are independent for different edges, which is crucial, right? Then if you look at any I or j, right? The expected number of successful matches they can participate in is at most 1. The first time they participate in a successful match, they leave the system, right? So the left-hand side is the expected number of successful matches that I participates in, right? Because Xij is the probability that I get set up with j, and independent of everything else, that match succeeds with probability Pij. So if I sum this over all j, that is the expected number of successful matches. That's at most 1. Similarly, the same thing for j. So again, the nice thing is that for every I, you have only one constraint. For every j, you have only one constraint. Right? And again, you can think of, I mean, if you have some patience, right, the patience will be one other constraint. So every I, you'll have 2 constraints, and every j, you'll have 2 constraints. One constraint for this successful matches and one constraint for failed matches. Again, given that you have only one constraint for every I, you can again round using Markov's inequality. Right? Solve the LP and round it using, they just take an arbitrary ordering of the edges and just use the LP policy on those edges in that order. Right? Analysis exactly the same as before. Another application is what is called Bayesian pricing. So here you can think of there are n items, okay, and you have one bidder or one agent, okay, and the agent has some values for each of these items. You are the seller, okay, and you have n items to sell. You don't know the value that the agent has for each of these items. All you know is the distribution of this value. So you know that for item j, the agent has a value which is drawn from xj, okay, and these xj's are independent for different items. Okay, so it's and if you're unhappy thinking about one agent, I mean, why would I want to sell to just one agent? You can think of this as being a population of agents, right? And the xj would be the distribution of the values in the population. It's an equivalent way of thinking about things. Okay, what do you want to do? So you have one agent, you have n items. The crucial thing is the agent wants only one item. He wants to buy one item. And his value for item j follows an independent distribution xj. The exact value is only known to the agent. The seller knows the distribution. So what's the policy for the seller? The seller can post prices for these different items. So he posts a price pj for item j without knowing the exact value of the buyer. He just knows these distributions and uses these distributions to set these prices. Now what the buyer does is he looks at these prices and chooses that item that maximizes his value minus price. Okay, that is his sort of utility that he gets. So the goal is to compute these prices pj for each item j, just knowing xj. The agent chooses the item that maximizes this quantity. The seller earns the price pj. Okay. Now the seller's goal is to maximize the expected value of what he earns, but the expectation is over these distributions. So, I mean, this problem is widely studied in operations research, where it's called under different names, and they use specific distributions. They are called the Gumbel distribution and so on. But the basic idea is this is a more sort of abstract setting of the same problem. Is the problem statement clear? So here there's no adaptivity in a sense. It's the complexity is coming because you have to set a price for each item. So the number of possible price vectors is exponentially large in the number of items. But for a given setting of prices, you can compute the expected reward quite easily.
So yeah, it has to be positive, right? The agent will choose nothing if all the bj's minus pj's are negative.
Oh yeah. So it is the max of this and zero. So if all the pj's are larger than the value, you just assume that the agent chooses nothing. So choosing nothing is also an option. Sorry. Okay. So there are various ways of thinking about this problem. Again, we can think of it in terms of LPs. Right? So you can say that, okay, look, let xjp be the probability that the price of j is equal to p. Okay, so you can think of there is some policy that is setting these prices. Okay, what is the probability the price of j is equal to p? I mean, this will be a 0-1 variable, but let's write it as a probability. Right? And yjpv is the probability that the price of j is p, and bidder the value of the agent for item j is v, and j is the item that is actually bought. Okay, that these three things have happened. Okay, let's call that yjpv. Okay, is this clear? Right. Now the LP constraints are, I mean, you could write many constraints, but here are the simplest constraints. Right? Every item has exactly one price. Right? The agent buys at most one item, and the agent buys the item which gives it the largest utility. Right? An even simpler thing to say is that the agent only buys the item if its value is larger than the price. Right? Whatever item the agent bought, its value better be larger than the price of that item. That should at least be true. It's a very weak constraint. Right? I mean, actually the agent buys the item that gives it the maximum utility. But we can't write that strong constraint as a linear constraint, so we'll write a very weak constraint. Okay, so what is the LP? It's very simple. The agent buys only one item. So yjpv was the event that the probability that item j has price p, the agent has value v for that item, and it actually buys that item. So if I sum over all this, that's the expected number of items the agent buys. That's at most one. The agent always buys at most one item. Right. Now for every item j, it can have only one price, which means that if I take these xjp values and sum them over all the prices, it must be 1. right? And this constraint is essentially saying that, look, if the agent bought item j at price p and his value was v, then two things must have happened. The price of j must have been p, and the value for j must have been v, and these two events must be independent, right? Because the seller is posting the prices before observing any values. And this constraint is only over values bigger than the price, because otherwise everything is, this quantity is just 0. That's it. It's a very simple LP. It's not encoding. It appears that it's not really encoding anything at all. All it's saying is that the agent buys only one item. Items have only one price, and this is just a natural constraint which is written for values for all values bigger than the price. That's it. Right? Turns out this is sufficient. This is all we need. And the way to see this is all we and the way to see it is to say that, okay, look, this LP looks horrendous, but once you take the dual, it has very nice structure. What is the dual? Right? So to take the dual, right? I mean, look at this constraint is for all the items. This constraint is for all the items. This is the only constraint that's even connecting the items together. Right? It's saying that, look, the agent only buys one item. Just take the Lagrangian of this constraint. So the Lagrange multiplier is lambda. Just take the Lagrangian. Now if you stare at this, right, I mean, maybe it takes a bit of time to stare at it and figure out what's going on. First thing is that these constraints are now for each j, so you can solve for each j separately, for every item separately. And what you can show is that for every item there will be only one price, okay? And this value will either be equal to this quantity or it will be 0. Right? So essentially what the LP ends up doing is finding a price. So you want to find a price for this item, right? You'll end up finding a price which maximizes this quantity. That looks like a mess. What it will do essentially is the following, right? So look at item j, okay? Look at the probability that the value of the item is at least p. So this is p, this is price p, okay? So this is the sort of the curve for the distribution of this value xj. So this is the probability that xj is bigger than this value p. Right? So you're given some dual multiplier lambda. What the Lagrangian optimizes is this area, right? Which is, take a price p, look at this area, and slide this pj from here to here. There's some point where this area is maximized. It will choose that point. Okay. So given a lambda, there's a nice closed form for computing this quantity pj, which is the price that is going to be set by the LP, the Lagrangian. So essentially the idea is the following, right? So for every Lagrange multiplier lambda, what this Lagrangian tells you is, what it gives you is one price for each item. And the price that it will find you is essentially that price that maximizes this area. Okay? So what the seller knows is this distribution. He knows this curve for the item j, right? And suppose you fix a lambda, what the Lagrangian gives you is this price pj that maximizes this area. So you get one price for each item. That's what the Lagrangian gives you. So now all you do is find a lambda such that if you take all these prices, the expected number of items bought by the agent is 1. Okay? That's it. Right? So it gives you a very, so there's a nice closed form for computing these. So given a lambda, there's a nice closed form for computing these prices. And now you just choose that lambda at which this constraint is satisfied. This constraint is satisfied, that the number of items bought is 1. So now, given this LP, what you obtained is one price for each item. And the constraint you have is that the expected number of items bought is 1. Okay. So you have one price separately for each item. And if you just sum up the probabilities that the agent buys those items, it's 1. Right? And now you just do the same rounding as before. You just do Markov's inequality and show that these prices work out. Okay. So I'm not going into the details, but it's all the same idea.
Yeah.
Why don't you need to put the constraint that yj pv is 0 when v is less than p?
I put it here implicitly. So yeah, I need to put it here. Sorry. Yeah, you're right. So that is crucial. So as you slide lambda up, this area, the maximum area you get keeps decreasing. So the sum of these areas have to be, the sum of these probabilities have to be 1. That's the point where you stop. Anyway. So that is about Bayesian pricing. And so you get a constant factor by just using this LP and taking its dual. It's a very simple LP.
This was just generalization of profit inequality, essentially.
So, yeah. I don't want to connect it too much because Matt is going to talk about it. But so what is known is that for that you can actually improve this constant factor, at least for because it's a pricing problem and the complexity is coming because there are exponentially many prices and there's no like sort of sequential decision tree aspect. It's a bit easier to show, to either derive better algorithms or to show complexity results. So at least for this problem, it is known that it is NP complete to compute the optimal prices. And you can get arbitrarily close approximations to the optimal solution for reasonable distributions. But the crucial thing here is that you do need that the distributions for different items are independent. If they are correlated, none of this works, and it actually becomes, you can't get better than a logarithmic factor approximation against the optimal solution. That is also known. And what is known for stochastic, I presented the stochastic knapsack problem before. Even for that problem, a PTAS is known in the sense that you can get arbitrarily close approximation to the optimal solution. Okay, so these are problems for which better algorithms than what I presented are known. So that was the second part where we saw that, okay, this Markov's inequality business and writing this LP over the expected values. I showed you a bunch of problems for which that technique works. So let me move to something somewhat different, which is sampling. So in sampling, the main idea is that, look, you have some big distribution. It has exponential complexity to maybe specify the joint distribution. But what if you could draw samples and write an LP over the samples? This is very vague, so let me be more concrete. Suppose the first problem is what is called two-stage vertex cover. And let me just define the problem. So you're given some vertices, and you're given some costs of these vertices. Okay. And now, but you don't know what the edges are. Okay. What you're given is a distribution D over what edges could be realized. I mean, maybe with probability 1/3, this set of edges is realized. Maybe with probability 1/6, this set of edges is realized, and so on. You're given a distribution D over possible edges that could be realized. Okay. But these edges will get realized only later, right? And when they get realized, these vertices will actually become more expensive to buy. Okay. So what you want to do, what a decision policy has to do, is it has to buy some vertices upfront, knowing only the distribution. Okay. So without knowing what edges are exactly going to come, it has to buy some vertices, and it pays those costs. And then it sees what edges got realized. So a set of edges from the distribution gets realized. And now it has to buy enough vertices to cover all these edges, to actually form a vertex cover. But after the edges get realized, the cost of all these edges increases by some factor lambda. So now if it has to buy edges, it has to pay a factor lambda more. So initially it bought the red vertex. Now suppose it buys this vertex to cover these edges. The cost it pays is CV because it bought this edge before, this vertex before, plus lambda times CU because it is buying this vertex now. Is the problem clear? So you can buy vertices cheaply without knowing what edges get realized. Then the edges get realized, and you can now, you have to buy vertices to form a vertex cover, but the vertices are more expensive. Okay. And you can generalize this to many stages. Maybe the edges get realized in stages. So decision policy is what vertices to buy in stage 1. Once you fix this, the vertices to buy in stage 2 only depends on what gets realized. That's an easy optimization. I mean, that's a standard optimization problem. I shouldn't say easy. And the goal is to minimize the total expected cost of the vertices purchased, but the expectation is over the distribution D, okay, or what is going to get realized tomorrow. Okay, so it's a Markov decision process with 2 stages, right? There's a first stage where you can buy some vertices. You have a bunch of actions to take, and then stuff gets realized and you have to buy some more vertices. So here the complexity is in the number of actions. There are exponentially many possible choices of what vertices you can buy. Again, you can write an LP, right? The LP looks somewhat different now. So XV is whether you buy a vertex or not in the first stage, right? And for every realization sigma, you'll have a variable YV sigma, which is whether you bought vertex V when sigma is a set of edges that got realized. So this is the variables encoding what you bought today, and these are variables encoding what you buy tomorrow, but what you buy tomorrow depends on what gets realized. Okay? So this is just the, sorry, this should be minimize, not maximize. So this will be the cost of the solution. You want a minimum vertex cover, which is the cost of the vertices you buy today plus lambda times the cost of the vertices you buy tomorrow. What you buy tomorrow is an expectation over what gets realized. Now you have exponentially many constraints because for every realization sigma, you need a constraint saying that you cover every edge in sigma. That either the first, so suppose the edge is u comma v, either u and v are covered, either one of u or v is covered in the first stage, or they are covered in the second stage if the edge E is actually realized in this scenario sigma. Is that clear? For every edge that gets, for every scenario sigma and for every edge E that gets realized here, you need a constraint saying that that edge is covered, either in the first stage or in the second stage. Now if the number of sigma is small, and you could explicitly write this LP down, then it's just like the LP for standard vertex cover. I'm not going to go into the details, but you can actually round it. You can solve the LP and convert these variables into integer variables, and that will tell you what gets realized in the first stage. That will tell you what to buy in the first stage.
So why is this a maximization problem?
No, it's a minimization problem. I said it's an error actually. It's minimize. Yeah.
Sorry, I'm missing something. Is there a fixed number that I have to meet, or?
No, the constraint that you have is that every edge has to be covered by some vertex. So for every edge, you either have to buy this endpoint or this endpoint.
Every edge that's being realized.
Every edge that's being realized.
So what stop, I mean, if I pick nothing in the beginning?
Then the solution might become very expensive because if this lambda is large.
No, even if I pick nothing in the beginning, some edges are going to be realized.
Realized, and I can decide to cover all of them in the second stage, but it might be very expensive because lambda might be large.
Thank you. I just thought the edges realized should be connected to the vertices I pick in the beginning. So
No, they are not connected. Okay. And but now suppose sigma is, suppose the distribution D is exponential size in the sense that it's like a gigantic distribution, and then I can't write this LP out because it has exponentially many, it will have a huge number of constraints and a huge number of variables. Right? I mean, though this looks formidable, suppose I only give you the distribution in the following form, that I can draw samples from the distribution. It's a black box access to this distribution where the distribution could be very complex. I may not be able to explicitly write it out, but what I can do is draw samples from this distribution. It turns out that is sufficient to solve this optimization problem. There's a nice structure in this problem that the second stage variables are all per scenario. Right? And you can think of using something like this is an expectation over a bunch of scenarios. You can think of estimating this expectation by sampling. The only problem is these constraints which are running over all these scenarios. Right? But it turns out, despite that complexity, there's a technique called sample average approximation, which is essentially just draw a few samples from this distribution, write the LP over those samples, solve it, and it will turn out to be good. Right? And the proof is essentially Chernoff bounds. It's not that different from Chernoff bounds. Right? And Anupam and others had a different technique where instead of doing this LP business, instead of solving the problem that way, you can think that, okay, the underlying problem is vertex cover. We know how to solve vertex cover without using LPs. Right? They develop a technique called boosted sampling, which essentially says, look, I know this distribution up front. Let me just draw samples from this distribution, just fake samples from this distribution. That will give me a bunch of edges. Okay, let me cover those edges in stage one. They are not the edges that got realized. They are just some samples I drew from this distribution. Just take those samples, that gives you a bunch of edges, cover those edges in stage one, right? Buy those vertices, and now wait for stage two, and whatever gets realized there, cover them with more vertices. It turns out even that works. And that works not only for and this kind of stuff works not only for vertex cover, but for many other kinds of covering problems. So a slightly different problem for which we can again do sampling, and this time without using an LP. It is something called stochastic Steiner tree. So again, so you have a root R, and you're given this graph, and you have some distances dij in this graph. So what is a Steiner tree problem, right? A Steiner tree problem tells you, okay, there's a subset of vertices, and you want to connect those vertices as cheaply as possible to this root R. So you want to construct a tree that connects that subset of vertices to R as cheaply as possible. That's the Steiner tree problem, right? In the stochastic Steiner tree problem, you don't know what vertices will get realized. What you know is there's some distribution d over vertices, right? And what you get is you get samples from D in an online fashion, and you want to connect those vertices to R. So k vertices arrive one at a time, drawn from this distribution D. The goal is to construct an online Steiner tree connecting those arriving vertices to R. Okay, and by online I mean that whenever a vertex arrives, we have to buy enough edges to connect that vertex also to R. And the technique again is just sampling. So what you do is run the algorithm in 2 stages. In the first stage, draw a bunch of samples from D, draw exactly k samples from D, okay, and construct a Steiner tree connecting the root to those k vertices. So basically, you start with initialize the solution not with the empty set, but by actually picking some samples from D and connecting those samples to the root. So you start with like a tree even before any vertex arrives. Okay, is that clear? So it's like just upfront draw samples and build a tree on it. Now wait for vertices to come. Okay. So the crucial point is that these samples that you drew are from the same distribution, so they're statistically identical to whatever input is going to come later. You draw k samples up front. Whatever k vertices are going to arrive are also going to be k samples from this distribution. Right. So that means that this tree you construct is roughly going to be whatever tree you wanted to construct anyway. I mean, that's at a very hand-wavy high level, right? So in the online stage, whenever an input vertex comes, connect B by the shortest path to this tree. Okay? And that will give you the online Steiner tree. So the analysis is essentially that the k points in the first stage and V, so take the vertex that has arrived, the k points in the first stage and V are a sample of size k plus 1 drawn from this distribution. Okay? So, and this V is like sort of a random vertex in that sample, right? So you can show that the expected cost of connecting V is roughly 1 over k times the cost of this tree, because this V is a random vertex among these k plus 1 vertices, right? So connecting it can't be very expensive compared to the cost of this tree. In fact, it's going to be roughly 1 over k times the cost of this tree, right? And that's true for every vertex that arrives. So just by linearity of expectation, the total cost that you pay is the sum over the vertices of this quantity, and that will be twice opt. But you pay twice opt to construct this initial tree, so the total cost you pay is 2 opt plus 2 opt, which is 4 opt. That's at a high level hand-waving proof, right? But there are some details, but that's the basic idea. So this shows, what I want to show is that sampling, even if you're given a black box access to a distribution, sampling is a fairly powerful technique. I mean, because when you draw a sample, what you have is something which is statistically identical to what you're going to get anyway.
To be sure, that works for any metric space?
I think so, yes. But you need to know k. If you don't know k, you can't get a constant. At least that paper doesn't get a constant if you don't know k. That's true, right? Not really. Okay. So another application of sampling is multi-item auction. So in the previously I showed you if you have one agent and n items, then it becomes, what we saw was a pricing problem. But you can generalize that to what are called auctions. So what is an auction? So you have many agents, many items, and what you want to do is allocate these items to these agents. Now what each agent has is a valuation for each of the items. So this agent has some valuation for this item, some valuation for this item, and so on. It could be more complex than that, but let's assume that's the case. And what the seller knows is what is the distribution from which these valuations are drawn. Okay? So the exact valuation is only known to the bidder, and the distributions for different bidders are independent. And the auctioneer only knows these distributions. Okay? And what we have to assume is that if you take a single bidder, then you can specify the distribution in polynomial size. Right? I mean, the entire running time depends on how complex is the distribution for one bidder. Okay? So for every bidder, he has some values for these items. They could possibly be correlated, but you know the distribution of these values. You know the same for this bidder, you know the same for this bidder. So what you want to do is design an auction that maximizes the expected revenue. So what is an auction? You want to, the bidders reveal what their values are. Given those values, the seller chooses, okay, who should get what and at what price. Okay. But there are some constraints, right? What you want the auction to satisfy is that the agent should reveal the truth. That if an agent reveals their true value, it maximizes their expected utility over what other agents are going to reveal. So what does utility mean? It means their value minus the price they were charged. Okay. So if I have value 10 for some item, I shouldn't report a value 20. In fact, reporting value 10 will maximize my expected benefit minus the price I pay. And it should be rational, meaning that the allocations and prices are such that every agent's value is at least the price that it pays. Right? I mean, if you don't want to allocate him something and charge him a huge price, because then his utility might be negative. Right? And this constraint need not be an expectation. It could be like, regardless of what else happens in the system, the utility of every agent has to be non-negative. But these are some, you can think of these as there are some constraints that the allocations and prices should satisfy. And subject to that, you want to maximize the expected price that is charged. Okay, but the expectation is over the distributions of the agent's values. So it is almost like the pricing problem, except that you have many bidders and many items, and you have these other constraints.
You assume that the bidders are additive, meaning when they get the value,
let me assume they're additive. So why is this easier? This is a bit easier than pricing because the algorithm that we designed will allow like the allocations and prices to be random. Right? I won't go into the details of this, but the basic idea is this. Right? You want to solve this. You want to solve this auction design problem, and the complexity is that, like, sure, I mean every agent's value is drawn from some distribution. You can specify the distribution, but now what the seller sees is the value of all the agents, right? And that could have exponential complexity in the number of agents, right? And he has to enforce constraints on whatever values are revealed, right? So the way to think about it is to have two kinds of variables, right? The first variables only depend on a particular agent. You can say that, okay, look, if this agent reported valuation V, what is the expected allocation he gets, where the expectation is over what everybody else reveals, okay? And what is the expected price he pays, right? That is one set of variables. These variables are polynomial in number because we are assuming that for a single agent, the number of valuations is polynomial. It's bounded distribution. Now you can have variables per scenario, and a scenario I mean, okay, what does everybody reveal together, right? So let's denote by eta a scenario. Okay, what are the allocations I make in this scenario, and what are the prices I charge in this scenario? The number of scenarios is exponentially large, okay, because the scenario depends on what everybody reveals. The n bidders, they are exponential in n number of scenarios. Okay. So now what do we want, right? So if you take these variables, right, these are the expected values, expected allocations and expected prices, right? We wanted the auction to be incentive compatible, meaning that for every bidder, if he reveals Vj, it maximizes his expected utility. You can write that as a constraint in terms of his expected values. Expected allocation, expected price. Right? And also, you want to maximize expected revenue, that again only depends on these expected prices. Okay? So those are constraints that you can write in terms of these variables. I'm not going to write those constraints out, they're easy to write. They're linear constraints in expected values. Now you have constraints per scenario, right? In every scenario, the allocations and prices have to be feasible. That what you allocate, I mean, you can't allocate one item to 10 agents. I mean, you have to allocate every item. Every item can get allocated to at most one agent, right? And you also need rationality, meaning that the price that you charge is at most the value the agent reveals. Right? So these are constraints that you have to enforce in every scenario. So you have these constraints per scenario. There are exponentially many of them. But these are the thing is that these are over different variables. Okay, and these per scenario constraints don't interact. For every scenario, you have different constraints. And then you have some constraints that couple these variables, right? I mean, the expected value, all this is saying is that the expected value, the expected allocation to J is actually the expected allocation to J. So this is the allocation to J in scenario eta. You sum over all the scenarios where the value was actually Vj, that must be the expected allocation. And similarly, the expected price is whatever the price he pays in the scenarios multiplied. They just take the expectation over the prices that he pays in every scenario. That must be the expected price. Okay, so all it is saying is that the expected value is actually the expected value. Okay, the hard part is that there are exponentially many of these constraints. Okay, but the number of these, so the exponentially many variables here. This summation is exponential size, but the number of these variables is not that many. I mean, there is the number of these capital X and capital P variables is small because they're only defined for every bidder and for every valuation. Okay. So what do we have, right? We have an LP where there are some constraints on these guys. For every scenario, there are some constraints on these variables. And now there are these constraints that couple the expected value variables to these per scenario variables. Right? And again, as before, we can take the Lagrangian. And we just take the Lagrangian of these constraints. Right? If you take the Lagrangian, what it boils down to is, so you just take you just have one Lagrange multiplier for these constraints. And if you put them in some objective, the Lagrangian actually decouples into two separate problems. Now there are no constraints coupling the per scenario variables to the expected value variables. The only constraints coupling were these constraints, and I've sort of put them in the objective, so they go away. Now there's nothing coupling this guys with this guys. Right? So what we get is an LP over the expected value variables, which says, okay, look, it has to be Bayesian incentive compatible, it has to maximize expected revenue, and blah, right? And then for every scenario, you'll get one optimization problem in the Lagrangian, and now you're taking the expected value over all those scenarios. Okay, so the Lagrangian objective will be some expected revenue plus something that depends on the expected allocations, plus the expectation over all scenarios of something that depends on that scenario. Right? Now you have an expectation over exponentially many scenarios. What do you do? Right? You just estimate it by sampling. Just sample a few scenarios, compute what would be the optimum there. And that's it. That's how you. I mean, so solving the Lagrangian is not that hard. You can just do it by sampling and Chernoff bounds. I'm hiding many details under the lug. It's actually not as simple as that. There are a lot of technicalities, but that's the basic idea. Now we can solve the Lagrangian easily. If I tell you the Lagrange multipliers, the problem decomposes into, okay, estimate this huge expectation for every scenario, you solve a separate optimization problem, and now solve this other optimization problem or just the expected value variables. Right? And given an efficient oracle for the Lagrangian, you can solve the original LP using many techniques. The original papers use the ellipsoid algorithm. So that gives you a polynomial time algorithm that computes an approximately optimal solution to Bayesian auctions. The basic idea is essentially, again, write this LP over exponentially many scenarios and estimate its value by sampling. But here, doing that on the LP directly doesn't work. If you take the Lagrangian, it works on the Lagrangian. Right? In the case of the vertex cover stuff, it worked on the LP directly. And you can do the same thing online, right? I mean, you can think of, okay, once you think of sampling, right, that sampling works, right? Then you can say that, okay, look, I don't even need to know the distribution upfront. As long as I think of have samples coming from a distribution, I can treat whatever I'm getting as input as samples from a distribution, so I can just estimate whatever I want to solve over those samples. Right? So in a sense, you can solve these kind of LPs online, even if the input is arriving IID from some unknown distribution. I have some unknown distribution, I'm getting inputs from it drawn IID. And I want to solve some LP over expected values. Right? As long as you can always treat your input as being samples. Right? And once you treat it that way, you can estimate whatever Lagrangian you want to estimate by just looking at what samples you got. Right? So a different way of viewing all this is to think of it as you can solve LPs online even if your input is coming IID from some unknown distribution. Again, all the details are under the rug, and this has many applications as well. But it's essentially the same idea. So in the final part of the talk, I'll discuss scheduling problems where the new aspect that arises is time. So far, none of the problems, I mean, we were designing decision trees, and it was important when you observed a variable and so on, right? When you opened a box was important. But somehow when we wrote the LP, all that disappeared. We didn't have any variable encoding time. Right? And these auctions and pricing, it was all one shot, so there was no time anyway. Right? But if you look at scheduling problems, time becomes important. So in stochastic scheduling, the simplest stochastic scheduling problem, you have m identical machines. You have n jobs. Every job has a processing length that is drawn from some distribution. These distributions are independent. And again, just as in stochastic knapsack, you can't find you'll realize the job length only after scheduling the job on a machine. When the job finishes, you know when it finished. Otherwise, it just keeps running. So this problem, there's no preemption. Once you schedule a job on a machine, it has to be scheduled there. And so what is an adaptive policy? An adaptive policy is an adaptive ordering of the jobs and a machines to assign them to. I mean, you take the first job, maybe you take a job, put it on the first machine. Take another job, put it on the next machine. Now maybe the first machine's job finishes, so you assign another job there and so on. So what is the order in which you assign the jobs to the machine? And your goal is to minimize the sum of the completion times, which is look at when the first job finishes, when the second job finishes, when the third job finishes, just add all of them up. Okay? And the expectation is over the job lengths are random, so the expectation is over the randomness in the job lengths. Okay, so maybe you place this job here and it took this long. You place this job here, it finished quickly, so you assigned this job here. Maybe it took this long, and so on. Right? So an adaptive ordering of assigning, adaptive order in which the jobs are assigned to the machines. So if the job lengths were deterministic, there is an LP for solving this problem. That LP actually encodes time. So you have variables Sj, which is when does job j start. Okay, so here everything is deterministic. So this is like sort of the standard machine scheduling problem where you know the job lengths and you're trying to assign them to machines. Okay. So this is a somewhat non-standard LP where Sj is the start time of the variables are Sj, where Sj is the start time of job j. Right? And what you want to minimize is the sum of the completion times. The completion time of a job j is whenever you started the job plus the processing length of the job. Right? That's when the job will finish. You're summing this over all job j. And this constraint essentially says that these Sj's can't all be too small. If I take any subset of jobs, if I look at roughly the sum of the Sj's, it has to be at least something that depends on the processing lengths. It can't be that all the jobs, I can't make all the jobs start at the same time because there are only m machines. Right? So that sort of lower bounds, some jobs have to start later because I can't put all the jobs on the machines at the same time. Right? And this is essentially capturing that. I'm not going to explain why this constraint holds, but essentially it says that, okay, look, Sj's can't all be too small. And you have to write this constraint for all subsets of jobs. It turns out if you do this LP is good enough in the sense that there's a way to round it and find a feasible schedule. But now your jobs lengths are stochastic. But the important thing to realize in this LP is that, look, if the distributions are independent for different jobs, when I start a job is independent of how long the job is going to take to run. Because when I start a job only depends on what has happened so far, and that only depends on the other jobs, but this job length is independent of the other jobs. Right? So you can think of if Pj is a random variable, Pj is independent of Sj. You can think of Sj as a random variable, Pj as a random variable, those two are independent. If that is the case, what is happening here is I'm just multiplying, here there's a multiplication, here I'm multiplying Pi and Pj, right? But if Pj is independent of Sj, I can take the expectation over all of this, even if Pj is like a random variable and Sj is a random variable. And that's all the LP does. Right? So now the variables are the expected start times, okay? And μj is the expected processing length, so the expected value of Pj, right? And all this thing is that instead of Pj times Sj, I can write it as μj times expected value of Sj, because these things I can multiply these things out. Right? And what happens here is just it's the expected value of this big mess, and it has some terms that depend on the mean and some terms that depends on the variance. Standard. Yeah.
Say for all subsets A of jobs, wouldn't that mean that you have an exponential number?
Yeah. So there are exponentially many variables in both these LPs, but there's an efficient. You can solve these kind of LPs efficiently because the number of variables is polynomial, and you can sort of, all you need to show is that there's an efficient separation oracle. So I won't go into the details of that, but you can use the ellipsoid to solve this efficiently. And the key point is that, look, once you write the LP for the deterministic case, the LP encodes time, but as long as you use independence, the same LP works for the stochastic case. Okay? And that's it. Once you write this LP and solve it, you're getting some expected start times, and that will give you the expected completion time of a job. It won't give you a feasible policy directly, but the rounding scheme is simply to schedule jobs in increasing order of, just order the jobs in increasing order of their expected completion times and just assign them to whatever machine is currently available. A lot of details, they're all under the rug. And these kind of ideas apply for some other problems. There's a variant of stochastic knapsack for which if you write such a stronger LP, it gives you, it solves other variants of stochastic knapsack. I don't have time to go into all that. So the final problem I'll discuss is something called the multi-arm bandit problem. And it's an ancient, I mean, it's a fairly old problem. It's from 74. I shouldn't call it ancient. It's a very classical problem. And the reason I'm presenting it is that it has this aspect of time, and the final algorithm for it is really beautiful. And I just want everybody to be aware that this algorithm exists. So the way to think about the multi-arm bandit problem is that you have what are called n arms. You can think of a slot machine as having n levers, and each lever is like a bandit arm. And each arm defines its own Markov decision space. So you can think of this being an arm, okay? And this arm has some states. Each state has some reward, and and there's only two actions in this state. You can either play the arm in this state or stop. If you play, the arm transitions to a different state probabilistically. You know these probability values, okay? Or you can decide to stop. So this is an arm and states of the arm. So you have n of these arms. This is the states for one arm. There will be corresponding states for another arm, and so on. Okay, and what you're given as input is this. Okay, what are the states for each arm, and what are the transition probabilities, and what are the rewards?
Sorry, then this probability 1 minus PAB remains at the same stage?
Oh no, sorry. There should be more. This is my laziness. There should be more actions. So maybe yeah, you can remain in the same state. That is allowed. So at each step, so you have n arms. Each arm is in some state. Okay. Suppose these are the states. The actions that are available to you is you can either play the first arm, or you can play the second arm, or you can play the third arm, so on. So you can play one of these arms. Whatever arm you play, its state transitions according to the transition matrix, and it gives its reward. Okay. And the arms that you don't play, their state remains the same.
And some of the PAB essentially would be 1.
Yeah. For each state, if you play the arm in this state, you transition somewhere. So the transitions out add to 1, and you're given all these numbers as input. Okay. So the crucial, what is called the bandit property, is that the state of an arm changes only if you play it. And at each step, you can only play one of these arms. So You want to find a decision policy for playing these arms. Okay. Suppose at time t you played some arm and this is the reward that you got. So let RT denote the reward that you get at time t. Okay. You want to find a policy that maximizes the sum of the RTs essentially. But that's an ill-defined problem because there's no time horizon. What you can say is that, okay, look, future rewards are less valuable than present rewards. So I have some discount factor gamma, which is less than 1. But there's no time horizon for the policy. The policy goes on till time infinity. And I'm maximizing the sum of what I call the discounted rewards. So the reward at time t is multiplied by a factor of gamma raised to t. So you value future rewards less than the current reward. This makes the problem smoother than having a sharp time horizon. Okay, that's the problem. So what is the policy? Given you have n arms, each arm is in some state. The decision of the policy is, okay, what arm should I play? Okay. So you can solve it by dynamic programming. The only problem is that the number of possible states is exponential. It is at every time each arm is in some state. So the number of possible overall states is exponential in the number of arms. And so for each of those I have to specify what action to take. So the non-trivial result is that there is a greedy policy that is optimal and it's computable in polynomial time. It's quite surprising that there's a greedy algorithm. So why is this surprising, right? I mean, why is this non-trivial? In fact, playing the arm, so you can say that, okay, look, let me play the arm whose current state has the largest reward. But that may not be the right thing to do because maybe an arm has very low reward now in the current state, but if I play the arm, it actually moves to a state which has huge reward. But maybe that happens 2 steps down. Maybe I play the arm now with some probability transitions to a okay state, and then I play it again, it transitions to a really good state. So this means the policy not only needs to take the current state of the arm into account, it also needs to know what's going to happen later if I play this arm. So a single arm, I only have 2 minutes. Maybe I'll go 2 minutes over. Okay. So fix a. So again the right idea is to use duality. Right. Let's take one arm and look at a cost version of the problem. So let's fix a cost lambda, and what you do is to say, okay, whenever you play the arm, you get the reward, but you also pay a cost lambda. Okay. So let vi s lambda is, okay, in state s. Suppose I start in state s. I only have arm I in the system. Okay. What is the optimal policy that maximizes the reward minus for every play I pay lambda? Okay. So the actions of this policy is it will keep playing the arm for some time and then decide to stop. Okay. So there's only one arm. I'm in some state. This is the start state S. A policy would be in every state of this arm, should I play or should I stop? And VIS lambda is, okay, what is the expected reward of the optimal policy? The start state is S, and for every play I'm paying a penalty of lambda. Okay. This you can easily solve because the state, for a single arm, the number of states is not that large. And the Gittins index is, okay, what is the largest penalty lambda? So as I keep increasing the penalty, right, I'll get less and less net benefit from this arm. And at some point, the optimal thing to do might be to not play this arm at all. Right? Because playing it, I'm paying so much cost that it's not worth it. Right? So the Gittins index is this value. Like I increase lambda such that this is 0.
Are you solving it by TP?
Yeah. So the Gittins index is essentially, okay, look, for any state of this arm, I ask, okay, look, suppose I keep playing the arm as long as the state is at least as good as what I started off at. Then what is the expected reward that I'm getting per step? Okay. So state has large Gittins index if either this state has high reward, so the right thing to do is to play in this state and then stop. Or this state leads to other states with large reward, so the expected per step reward till I stop is pretty high. Right? So it takes the long-term behavior into account. So in either case, this is a good state to play and it will have high Gittins index. So Gittins index is something that you define for every arm and every state of that arm. Right? Okay, what is the maximum per step reward I can get if I play in this state as long as I'm seeing states which are at least as good. And you can compute the Gittins index by dynamic programming. And the final policy is simply, if you're given a bunch of states, just play that state which has the highest Gittins index. And it turns out that's optimal. And this is a non-obvious algorithm. It's defined almost circularly, right? That the Gittins index is defined in terms of, okay, how much reward can I get from this state if I play long term, right? But then I have to only play if the state is at least as good as this state. But the at least as good as is defined in terms of the Gittins index again. So it's like somewhat circular definition. But despite that, turns out you can show this is optimal.
And this was known long time ago?
1974. There are many proofs that this is optimal. Anyway, there are other problems that I have not covered. I have not covered analysis of greedy algorithms. I have not covered dynamic programming, and so on. So in terms of open questions, how far can we push these LP-based techniques? I mean, I have done everything we have done so far is essentially analyzing non-adaptive policies. There are some analysis for adaptive policies, but not that much. There are several classes of problems that we don't really understand well. Machine scheduling, we did identical machines if they're not identical, or if there are other machine scheduling problems, the stochastic versions are not that well understood. Auctions, Bayesian auctions are fairly well understood at this point, but there are other variants you can think of, like auctions with budget constraints and so on. We don't understand them that well. And I have assumed independence almost throughout. If stuff is not independent but correlated, for many of these problems you need good models of correlation. So auction design is one of the few places where there has been success even with correlations. But beyond that, correlations make problems really hard, and you need good models for correlations. That's it.
Maybe in the interest of time, we'll take one or two questions and rest of it in the lunch break.
So the scheduling problem, shortest vector processing time first is optimal.
For parallel machines, not if you have preempt. I think even the deterministic version is NP hard for sum of completion time. So shortest expect.
Okay, it's optimal only for one machine.
Only for one machine, not for parallel machines. Maybe we should take it offline, but I think it is NP hard.
So in the last slide, what do you mean by bandit with neutral constraint?
Constraints on, so you can play a subset of arms every step, but the set of arms you play satisfies some matroid constraint.
You can get reward
from all the arms that you play.
Okay, let's take other questions offline. Thanks.